Hi guys, so today I'm gonna simulate the SAP-1 in a working circuit. I will discuss each and every component that made up the SAP-1 and how the data and operations flow from input to output. So I think some of you may seem this a little bit intimidating, but when I discuss it to you, bit the each and every component bit by bit, you will also understand it. So bear with me, guys. Ayan. So firstly, I wanna introduce to you uh, this two 7 segment display here. This two 7 segment display. Yeah. Uh, in this first segment, this number displays uh, the ROM stored here. This ROM is pre-programmed ROM that already has data in it. So when this number flows within this whole circuit, uh, it will output a certain number in this other 7 segment. Yan. So now let's take a look at this Excel sheet I made. As you can see below this example, this is the operation that we're gonna do in SAP-1. Yan. As you can see, the 5, 11, and 6 are the pre-installed data in the ROM, as I said earlier. And we're gonna flow these three numbers in the SAP-1 to produce the output 10. So in this box that I highlighted, these are the assembly code that we're gonna use to produce this operation in the example and get the output 10. So in the steps, there are 5 steps. Since there are 5 instructions, the steps should be 5. And every every step has 6 cycles called states that we're gonna point out when we later discuss the flow of the circuit. So in this memory address column, there are 16 available slots in that particular ROM that we use. And the blue highlighted ones are the ones that are occupied with either the instruction or the data stored in it. The instruction section, these are the code that we use to produce this operation. Yeah. And it is similar to coding in C, C++, Java, but this particular syntax is for assembly language. So in the machine code, the highlighted red ones are equivalent to the instruction of each syntax here, and the green ones are equivalent to the memory addresses here in the instruction section. Um, Getting to know the machine code of each and every syntax and memory address will be very handy later on when we discuss the flow of the circuit, since the data that will flow are converted in opcode or machine code, which is this number that you're gonna see. And since the machine can only read binary numbers from 0 to 1, or on and off, or true or false. And forgot to mention that the binary equivalent for 5 is this, and 11 is for this, and 6 is right here. Yeah. And later in the float circuit, I'm gonna write the value stored in the accumulator, and I'm gonna write this the final output of the operation. So let's go to the circuit. And so going back to the circuit, as I've said earlier, each and every step has 6 cycles or 6 states. So the each instruction will flow in 6 states before executing the next one. Usually, the program counter starts at 0000 here. So in the first state of step 1, the data in the program counter here is transferred to the MAR or memory address register. And here's the component AMR. Yan. As you can see, the value of the program counter is 000 and it is transferred to the MAR which is 000. Yan. Ayan. So, the value naman po in the AMR is the location of 08 in the ROM. Yan. Here. And as you can see here in the 08. Yan. 08. 8H. Then, and you can see it in the, it is flashed in the 7 segment and in the binary display of ROM here, which is 1000. And in the second state naman po, as I pulsate this clock, yeah, wait, you can see that the program counter is incremented by 1, which is now that the number is 001. And that's all that happens in T2 state. In the third state na naman po, the value stored in the ROM is now transferred into the instruction register, which is here. Yan. As the ROM is being transferred, as this happens, the 4 most significant bit, which is here, is transferred to the controller sequencer. Yan. Ayan. So let's pulsate the clock so we will see the results. Ayan. So as you can see, now the value are the same. And I break down this binary by half because this for most significant bit is actually the LDA. Yan. Or the instruction, and this part here is the data memory address of H8. Yan. Of 8H. Yan. Yan. So now you will be familiar with this instruction, which is here in the first step of the memory address, which is here. Yan. LDAH. Ayan. So the control sequencer here holds the different instructions to be signaled in the ROM. Yan. In here. To be signaled, and since 00 is applied here, we will load a particular data in the ROM. Yan. So, in here naman po, this significant bit of 1000 is transferred back to the AMR. Yan. We will see that as we pulsate the clock. Ayan. So, you can see now that the value of MAR changed from 1000. And now that the AMR changed from 1000, it will locate what the value stored in this particular memory address, which is 8H. And since it is here, yeah. So you can see that it is flashed in the 7 segment that the 5 is the data that is stored in the memory address 8H. Yan. So you can clearly see here in the assembly code that 8H has the data stored of number 5. Yan, so it's, yan. And so after that po, this number 5 here is now transferred to the accumulator, which is here. Wait. Which is here. Yan. This 5 is transferred all the way from accumulator A. And I'm gonna pulsate the clock to see it. Ayan. So as you can see, the number in the accumulator 5 changed from number 5. So it is now the value of the first accumulator. So I'm gonna write this here. And so the number 5 is now at the first number that the operation produced. Yan. In the sixth state naman po, nothing happens. Yan. As I pulsate the clock, yan, nothing happens. Yan. Napasobra lang po yung click ko, pero wala pa talaga mangyayari dyan. And I said this because T6 is reserved for a certain instruction later on in the circuit. So that is how the step 1 ends. And we will now proceed to step 2, which we will now execute this instruction, add 9H. Yan. And so starting from T1 to T4, the states from there are the same as the previous steps in step 1. So let me just demo it. So if we yan. So if we demo it, yan, yes. And you can see that the program counter change from 001 and the value of here as 19. And you can see here that the output from the ROM is transferred from the input register, and as I break down it, the value here is transferred to the controller sequencer, and here from the MAR is transferred to here. Yan. So the equivalent for 0001 is add, which is here, add. So add. Yan. And this controller sequencer here will signal add instruction to be the operand that we will use later. And as you can see here, the MMR will change to this. So as I pulsate the clock, ayan, the output in the input register here is transferred to MMR, and the MAR will locate the value in the ROM and flash what is the data that we will get from it. So 11 is the data located in memory address 10001. Yan. Now the state 5 begins. Yan. In the state 5, 11, the value 11 is now transferred to the B register here, all the way here. Yan. Since the accumulator has already has a value stored in it, it will automatically load to this B register, which is the buffer register. Yeah. So as I simulate it, it will transfer 11 to there. Ayan. So as you can see now, the number from this changed to 11. Yeah. So the buffer register holds this operand that will be used and added to 5 in the accumulator stored in it. Yan. It will be added because the controller sequencer signaled the ALU to have a addition operation. Yan. And as soon as the 11 is transferred here, it will immediately perform the operation in the ALU. So it will uh, add 11 to the value in the accumulator, which is 5. So the value will be and that value will be stored and replace 5 in the accumulator. Yan. And so 11 plus 5 is 16. So we will see the 16 here in the accumulator as I pulsate the clock. Ayan. Ayan. So as you can see here, the accumulator now holds the value 16. And to clarify po, wait, the uh, that the sixth state in step 2 is the transferring of value from the ALU to the accumulator A. So when the ALU or other subtractor finish at adding 11.5, 16 now will be transferred to the accumulator A, which is here. So that is the whole sixth state in the step 2. And so now we've completed na po halfway through the operation, which is 5 and 11. And now we will begin step 3, which we will perform this operation, subtract AH. Yan. Ayan. So to begin step 3 po, since starting from state 1 to state 4 are also the same, we will just gonna go through it by the demo. Ayan. So now, ayan. So the program counter changed from 10 to and stored in the transferred in the AMR, and we get the instruction from the ROM. We will get the data from the ROM, and it will be transferred to the instruction manager, which will break and transfer the other half to the controller sequencer and the AMR. Yan. So as you pulsate yan. So now we will get the value number 6 after performing state 1 to state 4, and this transferring of instruction is subtraction. Yan. So we will signal subtraction later in the ALU to perform the operation. And so in T5 state or fifth state, this value stored in the ROM is now will be transferred in the B register, and we will perform the operation after that. First we will simulate it, and so as you can see, the number from the B register change. The only difference here is that since the control sequencer signaled subtraction, we will perform subtraction in the ALU instead of addition. Yan. So after performing that, we will get 16 minus 6 equals 10. Yan. So 10 is the output from the ALU. And in 6th state, the output from the ALU 10 will be transferred to the accumulator A, which we will see in a second. Ayan. And so the value from the accumulator A changed from 10, and we will now update the value here, 10. Ayan, so that is whole the step 3 ends po. And in the beginning of step 4, wait, here, the state from T1 to T3 is also the same as in the previous states. So let me just simulate it. Ayan. So the program counter will start at incremented from 1 1, and it transferred from the AMR of 001. So it is now the data value in the ROM is 11000, and it's now begins transfer from the instruction manager. Yeah. And this is where the changes begin. After we break it down, after we break the instruction and transfer this most significant bit in control sequencer, you can see that this instruction is equivalent to output register, output instruction, rather. And since output is executed in the signaled by the controller sequencer, this will transfer the value from the accumulator A, which is 10, to the output here out in the output register, and we will finally see the value that will be outputted here in a 7-segment display. Yeah, so after I simulate it, yeah, so after pulsating the clock, the value from the accumulator A change is transferred to the output register and is now converted into a 7-segment display, which is number 10. Yeah, so this is the final output of the operation. So let me just change it. So let me just write the output. Yeah. Yeah. So as you can see, the the value from the accumulator is the same as the final output. In 5th state and 6th state, nothing happens because there are no other operands to be executed. Ayan. So as I pulsate the clock, nothing happens. Proceed to the last state, which is the last step, which is the state 5, which is we will halt now the application to stop from working. And the state from here, from state 1 to state 3 are still the same, since by simulating it, it will just increment the program counter and transfer the value of that from AMR and get the location of what address will be stored, and data will be transferred, and the ROM will be this kind of number 11111, and this value in the ROM will be transferred to the instruction register. Yan. And since this most significant 1111 is equivalent to halt syntax, which stop, we will signal the operation to halt or stop. So after executing this function, after pulsating it, we will no longer get any changes from this circuit, and it will stop working. Ayan. So as I pulsate the clock, nothing happens, even if I pulsate it a million times or 100 million times. Yan po. Ayan. So the program is now complete, and the value and we perform, and the procedure is a success. So we get the output 10 and executed every part of the program smoothly. Yeah. So thank you for listening.